Have you ever stopped to wonder what's really going on under the hood of an electric car when it just glides forward with that impossible smoothness? Or inside a factory robot that moves with, almost scary precision? The magic there, it isn't just in the gears and the metal, it's in these invisible, high-speed control systems that are constantly thinking, correcting, and perfecting every single moment. Today, we're going to pull back that curtain on one of the most fundamental and powerful ideas in all of engineering. Let's dive in. So yeah, it all really comes down to this one question. How in the world do these complex machines perform their jobs so flawlessly, thousands of times a day, without ever missing a beat? Well, the answer is this incredibly elegant feedback loop that works faster than we can even think. And that, right there, kicks off our quest for precision. Because at the heart of this whole thing is a system that's in a constant state of self-correction. It's like it's having a high-speed conversation with itself about what it wants to do versus what it's actually doing. And that whole conversation, that entire control loop, it all gets started because of one single super simple concept: a disagreement. A tiny little mismatch between the goal and what's happening in reality. In engineering, we have a name for that. We just call it the error. Okay, so how does a machine actually measure a disagreement? This is, without a doubt, the first and most critical step in this whole control process. Well, it's something we call the error signal. It's pretty straightforward, actually. The system is constantly doing this simple math. It takes the desired state, the speed you're asking for, and it subtracts its actual current speed. That difference, whether it's big or tiny, becomes the one thing that drives every single action the controller takes next. This diagram here, it's a perfect picture of the whole idea. Just look at the speed and flux commands. Think of those as the motor's marching orders, telling it both how fast to spin and how much muscle, or torque, to use. The system then measures what the motor is actually doing and feeds that information right back. The difference between those two is calculated in the speed flux controller, and bam, that creates the error signal that basically tells the system, hey, we're not quite there yet, time to adjust. So the system knows it's off, it has an error. Now what? Well, this is where the brains of the whole operation come into play, the controller. It has to take that error signal and figure out exactly what to do about it. And in the vast, vast majority of systems, that brain is a proportional integral controller, or as everyone calls it, a PI controller. Its whole job is to act as a compensator. It takes that error as its input, and using some really clever logic, it calculates a corrective command. And its one and only mission in life, to be so good at its job that the error eventually hits zero and stays there. Period. Now, here's what's so cool about how the P controller thinks. It kind of has two parts to its personality. The proportional part, the P, reacts to the present. If there's a big error right now, it hits it with a big, immediate correction. But the integral part, the I, that's the system's memory. It learns from the past. It adds up all those small little errors that have been hanging around over time. This is the secret weapon that gets rid of that tiny, annoying drift that the proportional part might just overlook. And that integral action, that's the real secret sauce here. Like this quote from the Power Electronics Handbook says, it's what guarantees you get perfect accuracy in the long run. So even if the motor's fighting against friction or a really heavy load, that I term will just keep nudging and adjusting until the speed is exactly what you asked for. No long-term or steady-state error. That's incredibly powerful. Okay, so our PI controller has crunched the numbers, it's processed the error, and it's made a decision. It spits out this nice, smooth voltage command. But how does a simple voltage command actually get a giant motor to spin? Let's look at how that decision gets turned into real-world action. Because that's the thing, right? A decision is totally useless if you can't act on it. And that smooth, analog voltage command from the PI controller, well, the motor's power electronics don't really speak that language. It needs a translator. And that translation job is handled by a device called a modulator. So first you've got the smooth command from our PI controller. The modulator then takes that command and compares it to a super fast, repeating triangular wave. And based on whether the command is higher or lower than the triangle wave at any given split second, it shoots out either an on pulse or an off pulse. And this is what comes out the other end. It's called a pulse width modulation waveform, or PWM. It's just a stream of digital on-off pulses. By changing the width, how long those on pulses last, the system can perfectly control the average voltage that gets sent to the motor, all while switching at a constant, really high frequency. So that's the absolute key right there.
This digital language of on and off pulses is exactly what the power inverter, the hardware that actually runs the motor, is built to understand. The PI controller gives the what to do, and the PWM modulator provides the how to say it.
So let's just zoom out for a second and look at the whole shebang. We have this elegant system that measures an error, calculates a correction, and translates it into physical action, all in a tiny fraction of a second. So what's the payoff? What does all this get us?
Well, what you get is a list of pretty incredible benefits. We get total elimination of any long-term error. We get a lightning-fast response to any changes, like when you stomp on the accelerator, and we get a constant switching frequency, which is fantastic for efficiency and making everything last longer. This combo is truly the foundation of almost every modern high-performance electric drive system out there. It's why that EV feels so incredibly smooth.
And I'm not just exaggerating. This isn't some niche, specialized technique. According to industry analysis, PID-type controllers, which include the PI controller we've been talking about, are used in an estimated 85 to 90% of all control systems. Think about that for a second. It's literally everywhere. This final diagram just ties it all together so beautifully. You can see the brain, the microcontroller, or MCU, generating those PWM signals. Those signals go to the muscle, the power inverter, which then drives the actual motor. All the while, sensors are feeding information back to the brain, closing the loop. It's just a perfect, self-contained engine of precision. When you really think about it, the PI control loop is one of the most successful and long-lasting ideas in all of modern engineering. It's just so simple, it's robust, and it's unbelievably effective. As we keep pushing the boundaries of what machines can do, it really makes you wonder, what's next? What will the next generation of control even look like? What comes after this kind of near perfection? Well, that's a question for another time.